Okay, let's get started. So as I announced earlier, we are going to have a lecture today, not a discussion section. And next Tuesday will be the discussion section. I'm not going to be here Tuesday, so I asked the TA to hold the discussion section. Okay? So we'll continue our discussion from where we left off last time. We were talking about processes and process management. So we went through various concepts, including this data structure called the process control block, or the PCB, which is what the kernel uses to track a process, state of the process, all of the information related to a process. And then I introduced system calls that you use to create processes, specifically the fork system call and the exec call that is used in conjunction with the fork. Okay? So if you have any questions about that, this is a good time to ask. The next lab is going to be on fork exec, for process management using fork and exec. So what we will do today is continue the discussion on process management and start talking about CPU scheduling. Okay? So I will introduce the notion of CPU scheduling. I will discuss why it is a useful concept to have in an operating system. And then we are going to look at several policies that the OS kernel uses to schedule processes on the processor. Okay? We won't go through all of that today because all of the policies, because it's a shorter class, it's a discussion section, but any overflow will continue next week. Okay, so let's start with what is scheduling and what does it do. Okay? So we are going to assume a multi-programmed environment. Okay? What that means is there are multiple processes that are in the system that are active at any given time. Okay? We'll assume that you have a uniprocessor machine, single core, and of the subset of active processes, some are in the ready queue. Okay, so that's your state transition diagram for processes. You have new, ready, running, terminated, waiting. You'll see that there is a queue associated with each state. That queue contains all the processes that are in that state at that given instant. Okay, so the ready queue will have a list of processes that are all waiting for a turn to run on the CPU. Okay. Now, processes that are waiting on I/O will be in the wait queue and so on and so forth. Okay, so that's the assumption. We have multiple processes active. Each process is in one of those 5 states at any given point in time. Okay. Now with that background, let's talk a little bit about scheduling. There are 2 kinds of scheduling that we encounter in an operating system. One is referred to as long-term scheduling and the other one is called short-term scheduling. Okay. Long-term scheduling simply means how many processes can be active at any given point in time in the system, so that the OS can service them in a reasonable manner, in an efficient manner. Okay? So in some sense, long-term scheduling imposes an upper bound on the number of processes you can start. When you hit that bound and you try to start a new process, the OS is going to refuse to start a new process, saying out of resources, either out of memory, or it will complain saying there aren't enough resources to start more processes at that point in time. Okay, that's the long-term scheduler. It keeps track of the number of active processes. It keeps track of the resource utilization on the machine, the amount of memory used, the amount of CPU. And whenever you are about to max it out, it says you cannot start any more processes, because doing so would be detrimental to the existing processes as well as the new process. Okay? So that is long-term scheduling. It determines the degree of multi-programming, how many processes can be concurrently active at any given time. Okay? Short-term scheduling, on the other hand, is where we are going to focus all of our attention. Okay? That's all I'm going to say about long-term scheduling. We won't study long-term scheduling in this course. All of our focus is going to be on short-term scheduling. Okay, and that's really the problem of all the processes that are sitting in the ready queue, waiting for a turn to execute on the CPU. which one gets to go next. Okay? So any policy that makes that decision is referred to as a short-term scheduler. The reason it is called a short-term scheduler is whatever process you pick is going to run for a short period of time on the CPU. Either it will do start doing I/O and have to give up the CPU, or as we will see, if you are allocating a time slot to that process, as soon as the time slot expires, the process has to give up the CPU and the scheduler will pick the next process to run. Okay, so this is referred to short-term scheduling. Okay? So basic idea is you will have a ready queue, as I showed you in the previous slide, that has a list of all processes or a queue of all processes that are ready to run. Pick one to run. Okay? And the policy that does that is referred to as the short-term scheduler. Okay? Now, the short-term scheduler will run at various points in time. Okay? There are three conditions that are listed there. When any of those conditions are true, the CPU scheduler is going to run. Okay? So when a process is going to switch to wait state because it starts doing I/O, the CPU becomes idle. The process was running, starts doing I/O, goes to wait state, CPU is idle. Short-term scheduler runs to decide what goes next, which process goes next. Yeah, or an interrupt occurs in the system. The process that is running is suspended. Its state is saved in the PCB. The OS is going to run an interrupt handler, and when the interrupt has been handled, again the CPU is idle. The OS has to decide what process needs to go next. Okay? And the third one is whenever a process is created or terminated, you have to decide what to do with the process. Does it get to go run on the CPU or is it going to go in the ready queue? Okay? So those are three conditions, at least three conditions that where the CPU scheduler actually has to be invoked and has to make this decision. Okay? There's one more and I'll talk about it. Okay? So before we do that, let's define two terms. One is called a non-preemptive system and the other is called a preemptive system. In a non-preemptive system, the CPU scheduler must wait for one of those three events to occur before it actually runs. Okay? Either the process must give up the CPU by doing I/O, or there must be an interrupt in the system, or a new process arrives or an existing process terminates. And any of these conditions are true. If the scheduler runs, you have a non-preemptive system. Okay? In a preemptive system, all of those conditions, any of those conditions could be true. In addition, as the term preempt suggests, the CPU scheduler may force a process to give up the CPU, can preempt a process from running. Okay? And most preemptive systems use what is called time sharing or allocate time slots to processes. So whenever the time slot of a process expires, even if none of those conditions are true, it is not done on any I/O, no new processes have arrived or departed, or an interrupt is yet to occur, even if none of those are true, when the time slot expires, the CPU process has to give up the CPU. This is a non-preemptive system. Okay, you can force a process, or you can interrupt a running process and force it to give up the CPU. Okay, yes, question.
Why would you want to stop processes to run, and what would you use it for?
Okay, the question is, why would you want to make a process give up the CPU and what would you use it for? Right? So let's take a simple scenario where you have started two applications. So let's say you're running your browser and you're running your mail client. Okay? Two applications running. Okay? Both are active. Okay? Now, in order for both of these to make progress, they need to take turns executing on the CPU. Okay? And the way this is going to occur is you'll give a little bit of CPU time to process one, and then it will run for some period of time. Then you'll switch to process to give it some time, and then maybe there are other processes. So you'll cycle through them. So each gets a little bit of time on the CPU, and as a result, all of these processes make progress. Okay? If you have only one processor in your system, which is what we have assumed, this is the only way you are going to allow all processes to make progress. Okay? If you have multiple cores, these processes could actually run in parallel. Okay? But typically, you have more processes than you may have cores, so you will still have to do something that allows each process to make progress. So you are going to give them time slots, allocate time slots, and each of them is going to run for a short period of time, and the next one. So from a user's perspective, it looks like all the processes are active. Your mail client is reading mail, and you can use your browser to visit web pages. All of those things can be done concurrently. Okay? So you don't see that only one application is running, other one seems to be out. So that's what allows you to, that's what the OS does to allow processes to make progress. Okay? So most of the systems we will see are preemptive in nature. We will look at some non-preemptive CPU scheduling algorithms as well, just because they're much simpler and easier to understand. Okay, but by far most of the scheduling algorithms or policies are going to be preemptive in nature. Okay. Now, before you decide what policy to use, and what basis are you going to make this decision, and what process runs next, you have to decide what are you trying to achieve for your system. Okay, what is the goal you are trying to achieve? And this slide is going to list several goals, all of which seem like good goals to shoot for. Okay. The first one says that you can try to optimize or maximize CPU utilization. CPU utilization is simply the percentage of time the CPU is busy. The more you can use the CPU, the better you are in the system, because more processes are making progress by using the CPU. Okay. The second criteria is you could design policies that maximize throughput. Okay. Throughput is the number of processes that finish per unit time. And what is the rate at which processes are completing in your system. Okay. That's another good goal to shoot for, especially if you have batch application. The more jobs or tasks you finish per unit time, the better you are in your better performance application C in your system. Okay. Third is the turnaround time. Okay. That's the time between when a process starts doing I/O or not I/O, when it starts executing in the system and when it actually finishes. Okay. That's the turnaround time, and you can try to minimize turnaround time. You can try to minimize wait times, which is anytime you do I/O, the time you spend in the wait queue waiting for the I/O to finish could also be minimized. This allows you to make more CPU progress and spend less time waiting for something to happen. Okay. So this allows you to have a more responsive system. Okay. And you could also minimize response times, and response times are useful in interactive jobs. And that's the time from when you provide an input to the time when the process begins to respond to that input. Okay. So when you click on a mouse, how long does it take for the system to respond by showing a drop-down menu or whatever that click will allow the system to do? That's referred to as response time. Okay. So you may want to minimize response time, so you see a more responsive system. The system doesn't seem slow or sluggish. Okay. So all of these are good goals to shoot for, and ideally if you could come up with one policy that optimizes all of them, then life is good. But unfortunately, many of these policies conflict with one another. Okay. When you try to optimize some, it is often at the expense of some other matrix. So you have to decide which ones are important for the system. Okay. And what is it that you are going to optimize? That's what is mentioned in this slide, saying you could try to optimize all of these policies, but typically this is not possible. So because one comes at the expense of another. Yes, question.
Is turnaround time the time from ready to terminate it, or new to terminate it?
The turnaround time is the time from when you start the process to when you terminate. Okay? Meaning if you start at noon and you finish at 1 o'clock, that turnaround time was 1 hour. Okay? Yes.
Is the start time for a process determined by when the process is in the new state or when it's first in the running state?
Okay. The start time of the process, we didn't define what a start time was. We use a term called arrival time, which is going to be similar to the notion of a start time, and that's the time at which the process arrived in the system. Okay. That's when basically, let's say you double click on an icon that starts up that process. So the time that you did this double click event which spawned the process will be referred to as the arrival time of the start time. So that's how we are going to define it. We'll define all of these terms more carefully. Okay, but what you need to understand is, first of all, your CPU policy could be designed to optimize some of these metrics, but not all of them. Okay, they are all good goals in some way, okay, for some system or the other. But most policies will not optimize them all. They will try to optimize some of them. So then the question becomes, for a particular system, which of these criteria is more important? What does the user and their applications care about? And you have to pick a policy that optimizes that metric. And we'll see different policies that are going to optimize different metrics. Okay. So we are going to make the following assumption. We'll assume that your uniprocessor single core system, multiprocessor scheduling algorithms are a lot more complex. We are not going to study them here. That's a graduate level material, okay? Graduate level course material. We'll assume one process per user. We are assuming for now that you don't have multi-threaded application. It's a simple process which is only one thread. And we'll assume further that processes are independent. They're not cooperating processes that require specialized policies. So a very simple system where there's one processor. Okay, there may be multiple users. Each user has one process. That process is single-threaded. Okay, so these are the policies we are going to look at. We are going to start from very simple ones. The first one is going to be first come first serve, or FCFS, very straightforward policy. Then we are going to look at one called round robin, as the name suggests, it's going to cycle between processes. And then we are going to look at some other shortest job first, multi-level feedback queue, which we will probably get to next time. I may start talking about that today. Is the policy that is used in most Unix-like operating systems. Okay? It's called MLFQ. We'll come back to that and see. It is going to build on some of the earlier policies like shortest job first and round robin. And the very last one is called lottery scheduling. This is a probabilistic scheduling algorithm. It uses probabilities, and we'll see how that works as well. So we are going to go through all of these one at a time. Okay, so that's basically just a snapshot of what's coming. Okay, so let's start with the first one. Okay, first come first serve. Also called the FIFO policy, very straightforward policy. Okay, the thing, what this policy does is it executes processes in the order in which they arrive in the system. First come first serve. Process A arrives first, it gets to run. Okay. And it is a non-preemptive policy, which means once the process starts running, it runs until it's either use up the CPU because of I/O or it finishes. Okay. And it can run for as long as it wants. The CPU is not going to be interrupted by the OS because it is a non-preemptive technique. Okay. So processes come in some order into the system, they are queued up, and they get to execute in the order in which they are. A very straightforward policy. We are going to look at this in a little more detail. Here's a picture that shows 3 different arrival orders. Okay, the first one shows the x-axis is time, so it shows B is arrived first. Okay, it gets to run. It runs for 2 units of time. Okay. And then C arrives somewhere before B finishes, it gets to go next, it runs for 3 units of time, and then A gets to run. So the arrival order was BCA, the order in which they run is also BCA. In this case, the process is running to completion. There's no cycling between processes or anything like that. This is a non-preemptive system. Right? That's another one that shows if they arrive in some other order, they would also execute in that arrival order. Okay? And so on. Now, one problem with this policy, so the advantage is very straightforward policy. So there's not much to decide. You just queue processes up in the order of arrival and execute them. Okay, the main disadvantage is that it could lead highly variable wait times. Right? Because you are executing jobs in arrival order, first come first serve order, if a long task just happens to arrive before a short task, the short task is going to wait for a long period of time before the long job finishes. Okay? And the waiting time is going to increase in your system. If the arrival order was flipped, right, the short job arrived just before the long job, the short job would run quickly, it would finish, and then the long job would run till completion. Okay? And the long job didn't have to wait as long because the short job took a short period of time to finish. So the arrival time is highly variable. It depends on the order of arrivals. And if some long jobs arrive, they can hold up short jobs. Okay, similar to if you're driving on the freeway and get stuck behind an 18-wheeler, everything slows down. Okay. So the same thing is true here. Okay, that's the intuition. So waiting times highly variable. Okay. That's a disadvantage. It also leads to poor overlap of CPU and I/O. I won't stress this as much, but the point is CPU-bound tasks will force I/O bound tasks to wait. And why this is the case will become clear when we talk about multi-level feedback. So it happens that I/O bound tasks are your short jobs. They run for short periods of time and they go back to doing I/O. Okay? CPU bound tasks are the long tasks I was mentioning. These are jobs that run for long periods of time. So if an I/O bound task arrives or becomes ready to run just after a CPU bound task started executing, it would have to wait for long periods of time. Okay? It's better to run that short job and have it go back to doing I/O than make it wait for a CPU bound task to finish. Next question.
Just a question about the previous slide, actually. Where you have in the third example, you have A restarts. That's once B is completed, not once the I/O is completed, correct?
So I didn't show I didn't mention the third example. Since there's a question, I'm going to go through that in just a little more detail. So the arrival order here is A, B, and C. Okay, but in the first two examples, there was no I/O. Tasks ran, they ran till completion. Okay. In this example, task A is actually going to do I/O. It arrives first. It runs for 2 units of time. It starts doing I/O. Now it goes on the wait queue. Okay. So the ready queue has the other 2 tasks, which is B and C. Okay. So then B gets to run next. Okay. So B runs to completion. It's a CPU bound task. And in the time that B is running, the I/O for task A has finished. It comes back to the ready queue since it arrived before C. It gets to run next. And then it finishes. And then C, which arrived last, runs last. Okay. That's the scenario here.
Okay, so you wouldn't have A interrupt B once the I/O is complete.
What was the question again?
So you wouldn't be B runs until A's I/O completes, and then A interrupts it?
Yeah. So in this case, you cannot interrupt tasks. They can give up the CPU by finishing, or by doing I/O. Okay. But one task cannot interrupt. That's what a non-preemptive system is. Non-preemptive means you cannot preempt a task. Once it gets the CPU, it owns the CPU until it decides to give it up or it finishes. So even if A has become ready to run again, it cannot interrupt B. Okay, because it gave up the CPU. It has to wait for B to finish, then it gets to run.
Okay.
Okay, so now we'll do an example here. A quick example which is for round robin, not round robin. We didn't do round robin yet. Okay, so let's do round robin scheduling and then we'll do an example that compares FCFS and round robin. Okay, so round robin scheduling algorithm, another simple algorithm. As the name suggests, here tasks or processes are going to take turns in round robin order. Okay. This is going to be a preemptive scheduler, okay, as opposed to FCFS, which was non-preemptive. In this case, tasks or processes are going to be given time slots, okay, also called quantums. Okay. So when a process gets to run, if it uses its time slot, then it has to give up the CPU. So your turn is up, it's for time for something else to execute on the CPU. If it was running and it decides to do I/O in the midst of its time slot, then it has to give up the CPU in any case. Because it had a shot at the CPU, it decided to do I/O, it's gone to the wait queue, it cannot run anymore. Okay. So whenever a process executes, it's either going to use up its time slot or it is going to do I/O in the midst of its quantum and relinquish the CPU. Okay. In either of these two cases, then the next process is going to run next and so on. So if you have 3 processes, they will run A, B, C, and so on, unless some process is off doing I/O, in which case you'll just cycle through the remaining processes. Okay. Yes, question.
But what happens if we have a time slot and the process that was running terminates? Does that also count towards the round robin that just circulated?
So question is, what happens if you had a time slot and the process terminated? So if a process was executing and it executes its last instruction and terminates, it also gives up the CPU. Okay, so if you have an interrupt, you give up the CPU. If you do I/O, you give up the CPU. If you terminate, you give up the CPU. Okay, or if your time slot expires, you also give it.
So in case of termination, we don't have to wait for the quantum to end. We can just
We can
relate
any of yes. If you have an interrupt, you don't wait for the quantum to end. If you do I/O in the middle of a time slot, you don't wait for the time slot to end. If you finish, you don't wait for the time slot. Okay? If your CPU bound are executing, none of these things occur, then you wait for the time slot to end, then it will. Okay? So essentially, the way this algorithm works is you are going to use a timer. Okay? So the CPU scheduler says A gets to go next. A starts executing. It sets a timer. Okay, and the length of the timer is the duration of the time slot, which is also called a quantum. And it will run for a maximum of the quantum. Okay? If you do I/O or the interrupt before then you'll give up the CPU. Otherwise, you'll run through the end of the quantum. Timer goes off. CPU scheduler runs again, picks another process, sets a new timer, and so on. Okay? So this is round robin. Now there are some interesting design details. The first one is, how do you decide the length of your time slice or time slot? What considerations might an OS designer use to guide their decision? Okay. Now we will not say if you should pick X. What we'll see is what are the trade-offs if you pick it too small versus too large. Okay. So if you pick a large time slot, what is going to happen is waiting times are going to increase because each process has to wait for longer before it gets a turn at the CPU. So if there are 5 processes and you pick the time slot of 1 second, the 5th process in the queue has to wait for 5 seconds before it gets a shot of the CPU. Then another 5 seconds before it gets the next shot and so on. So the longer your time slot, the higher the wait times. Okay? Now as the time slot keeps increasing, this round robin is going to degenerate to FCFS. In the limiting case of the time slot is set to infinity, okay, round robin is no different from FCFS because the time slot is never going to expire. You will run to completion, which is exactly what FCFS does. Okay? So as we make the time slot larger and larger, the behavior of the round robin policy starts approaching that of FCFS and starts seeing all the same limitations of FCFS. Okay? So this suggests that the time slot shouldn't be too large. Now if you make it, yes, question.
So with FCFS, when A finished, it got put on the queue ahead of C. But in this instance, when it finished IO, in this instance, when it finished IO, it would be put at the back, right?
Yes, so in this case, you are doing round robin.
So
if you do IO and you become ready to run, you go to the end of the queue because there is no such thing as arrival order anymore.
Right, so it's not exactly the same in the case of IO.
In the case of IO, you could, of course, say in FCFS, there is no definition of what you do for IO. You could say that the arrival time is whenever you become ready to run.
Sure.
In this case, if IO finishes, you go to the end of the queue. The arrival time is defined as the time you actually arrived in the system, then you get a slightly different variant of FCFS. The variant I showed you defined the arrival time to be the time of arrival in the system. In this case, it's defined to be when you become ready to run, in which case you go to the end of the queue because you are the most recent task. Okay, so now let's look at the scenario where the time slice is small. Okay? The smaller you make the time slice, the lower the wait time. In particular, if you pick a 1 millisecond time slice, every process gets to run, if there are 5 in the system, every 5 milliseconds you get a shot at the CPU. So that's good. But on the other hand, smaller the time slice, more context switches you are going to have in the system. There's more switching. And if you have 1 millisecond time slice, you are going to have at least 1,000 context switches in the system at a minimum if every process uses all of its time slice. If you had 100 millisecond time slice, there are only going to be 10 context switches every second. If you remember last time when I talked about context switches, I said that's an expensive operation. It is an overhead or burden on the system. The OS has to save the state of the registers in the PCB, load the state of the new registers. All of that is extra work. Okay, so you want to amortize that overhead for as large a time slice as possible. Okay. In particular, let's say it took you 1 millisecond to save registers and reload the new register. If you set the time slice to 1 second, you'll run for another 1 second. Okay, then you give up and you waste every 1 millisecond, you're going to waste another millisecond. Okay. So the larger the time slice, the more amortized your context switches are going to be. Okay. This suggests that you shouldn't make the time slice too small either. Okay. So making it too large is very time degrade. Making it too small, context switch overheads start weighing on the efficiency of your system. You start paying higher and higher taxes in the system. So you want to pick something that balances these trade-offs. And now what you actually pick ends up depends on what CPU you have, what operating system you have, and so on. But by and large, most operating systems might pick time slots that are between 10 and 100 milliseconds. Whenever a CPU is given to a process, it gets to run for anywhere between 10 to 100 milliseconds before it gives up the CPU. Those are typical time slices that are used. Some may use as small as 1 millisecond. As processors get faster. Okay, context switch overheads could vary from anywhere from a tenth of a millisecond to a millisecond. So you want to reduce the overhead of context switches to as little as possible. Okay, question there, yes.
Is it possible to round off scheduling that has like variable time slices, or does it have to be all set with the exact same time slice, like externalizations?
So question is, can you have round robin policies that will have variable time slices? This policy uses fixed time slice. When we come to multi-level feedback queue, which generalizes round robin, you will see that you can actually have a round robin with variable time slices. But that's a different policy. It's no longer called round robin. Okay, but it does something like round robin. But for now, assume that the time slices are fixed and they don't change. Okay, so we'll do example 1, which is simply going to tell you how these policies treat some jobs. So here I'm going to use the term job in a generic way. It could mean a process or a thread. At this point in time, I've only encountered processes, but also many of these policies apply even for scheduling threads, which is why I'm going to use a more general term called a job. It can apply to either. So here we have 5 jobs. Each of them has a length of 100 seconds. Okay? And we are going to assume that the time slice for round robin is 1 second. Context switch overhead we are going to ignore and set to 0. In reality is not 0, but here we are just going to ignore it altogether. Okay? So then the question is, at what we are going to see how FCFS schedules these jobs, okay? And how round robin schedules these jobs. And at what points in time are they going to finish? Let's start with FCFS, straightforward policy. So FCFS is going to schedule them in the order. Let's assume they arrive in order 1, 2, 3, 4, 5. Okay, so one arrives first, it gets to run first. Okay, so it starts at time 0. What time does it finish? So it's going to finish at 100 because it needs 100 units of CPU time. Okay? And at time t equals 100, job 2 is going to run. It's going to run for 100 seconds. That's its length. It's going to finish at time 200. 200, job 3 is going to run. Yeah, that's going to take another 100. It's going to finish at 300 and so. So at time t equals 500, all 5 jobs are finished. Each has taken 100 seconds of time and they've run in turn. Okay, so that's FCFS, straightforward. And now let's look at round robin. Okay, so let's see how round robin is going to be. So what's the time slice? It's 1 second. So each job, they're all arrived at time 0. Okay. Each job is going to get 1 second of CPU time and you're going to cycle through it. Okay. So at first second, job 1 runs second at t equals to job 2 runs for a second, 3 runs at time 3 equals to 3 and so on. Okay. So you are going to continue to do this, and then if you did that, when would a job finish? Yes?
Between t equals 100 to 105, I think all the jobs are finished, right?
T equals what?
100?
100. Okay. So at t equals 100, let's see how many time slices have elapsed. 100 time slices have elapsed. Each of these jobs have gotten a fair equal share. So each of them have gotten 20 seconds of that time. Okay, so of their 100 seconds, they only executed 20 of those seconds. So there are 80 more seconds to go. Okay? And the question is, when does the job finish? There's many times of this.
500.
Okay, so they are all going to finish at 500, but they will not all finish at 500. Okay, so the last job is going to finish at 500.
Yeah.
Question is, when does the first job finish?
So
496. Okay, so you will have to see job 1 is going to basically get its 100th second of execution time at time 495 and it finishes at 496. Okay? And then job 2 finishes at 497 and then so on and so forth. So I'm going to show you this. Okay, so basically you will see that there's a big difference in the completion times here. Okay, so here job 1 finished at time 100 and job 5 finished at time 500. So the big difference in completion. Here your fair policy, they're all finishing within 5 seconds of one another. They all arrived more or less at the same time. Actually they arrived at the same time. They all finished at the same time. Okay, so the average completion time here is 498. That's the average of these 5 values. Okay, is that clear? Okay, so I'm going to talk about this column in just a moment, but is it clear how we sort of ran through this example and made sure we know when each of these job finishes? Okay, so completion time is what is shown there. Then the question is, what is the wait time? Wait time is the time you actually spent waiting in the system. Okay? So take a job that arrives at time 0. It finished, let's take the first job. It arrived, finished for 496. Time t equals 496 seconds. Okay? And between these 2 points in time, it executed for 100 seconds. That says job length. So what is the time it was spent waiting in the system? Okay, so it should be 396. Of this 496 seconds of its lifetime, it executed for 100 seconds on the CPU. Everything else was spent waiting. in particular is waiting on the ready queue, waiting for its turn again. Okay, so I'm going to give you a formula which is going to tell you how to compute this. So wait time essentially completion time minus so if you take the difference of these two columns, you should get wait times if they all arrived at time 0. Okay, so you take 498, this finished at this time, it executed of that lifetime, it executed for 100 seconds. So the rest of the time was spent waiting. Okay, so basically, and then if they don't all arrive at 0, then you have to basically do this. So completion time minus job length minus arrival time, okay, will simply give you the wait time. That's the of the lifetime you spend in the system, you take out the CPU execution time. Okay, the lifetime is always completion time minus arrival time, and that gives you the wait time. Okay. So now you can see what's happening here. Okay, so wait times again go from 0 to 400. Okay. Job 0 in FCFS didn't wait at all. It arrived and it got to execute immediately. Okay, it finished at 100 and it ran for 100, so there's no waiting. Job 2 had 100 seconds of wait time. Job 3 has 200 seconds of wait time, and so on. Okay, in case of round robin, again it's all fair, and they all wait for approximately the same amount of time. Okay, so round robin is a more fair policy as a result. Okay, in FCFS you are going to get a lot of variations. Okay, we'll quickly run through another example. Okay, so here job lengths are not identical. Okay, they are different. They are going to basically vary. Job 1 has length 50, job 2 has length 40, 3 has 30, 20, and 10. Again, they all arrive at time 0 in that order. And then you are asked to see what is the completion time and what is the waiting time. Okay, I'm going to do this example as well. But in future, you may get homework assignments of class exercises that ask you to run through these examples. So let's look at FCFS. Okay, which job finishes first and at what point in time?
First one at 50.
Okay, first one is going to execute first, and it's going to execute for 50 seconds. It's going to finish at 50. Okay. What happens next?
Job 2 executes and finishes at 90.
Okay, job 2 is going to go next. It's going to execute for 40 seconds. It's going to finish at 90. Okay, it's FCFS. So then job 3 is going to run next. It's going to execute for another 30 seconds. Going to finish at 120. Then job 4 runs. It's going to finish at 140. Job 5 is going to finish at 150. Okay, so that's just the easy part. Now we have to do round robin. Okay, again, same scenario, 1 second time slice. Each of them is going to basically run for a second and give it a turn to the next job. Okay. So the best way to work through this example is to basically look at what's happening every 5 seconds. There are 5 jobs. Okay. So every 5 seconds, each of them has run for a second. So you decrement how much more time you need before you finish. Okay. So in this case, the 5th job is the shortest job. Okay. After 10 iterations, 10 round robin cycles, it's going to finish. And it will be the first job to finish because it has gotten 10 turns and the CPU, each turn gets it 1 second, it finishes 10 seconds. Okay. So the question is, when do 10 cycles finish? Each cycle takes 5 seconds. Okay. 10 cycles is going to take 50 seconds. So that's when that job is going to be done. Okay, so now it's done, so it's gone. Okay. The other jobs still have to execute. Okay. At that point, you have to decrement 10 from each of the jobs because they have each gotten 10 seconds of execution time. That's a time cycle. So now you are going to round robin between those 4 jobs. Okay. So then basically this job, so you will do the same thing. Okay. And then after 10 iterations of round robin, this job is going to get an extra 10 seconds. It's going to finish next. Okay. The first 10 cycles, it got 10 seconds, and the next 10 cycles is going to get another 10 seconds. This job will be done. Okay, it's going to finish. Then you do round robin between the 3 remaining jobs. Okay? You do the same thing until this 3rd job finishes. Then you do round robin between those 2, and so on. Okay? That's how round robin will execute. If there are no new arriving jobs, you will basically keep doing this until all jobs are done. Okay, so if you run through this a little bit carefully, you will see that you're going to get those completion times. We said after 5 of these iterations, you're going to finish at 50. This is going to finish at 90, 120, 140, 150. Okay, so the completion time average in this case is the same. Okay? And the wait time is basically this. You take the completion time column, you take the length, and you take the difference between the two. The arrival time is 0, so you can ignore it. So 150 minus 50, the completion wait time is 100. Okay, this job finished at time 150. Of that, it spent 50 seconds executing. The other 100 seconds were spent waiting. Okay, that's what that is saying there. And you will see that they basically computed and you'll get all the wait times. Okay, any questions on this? This is a little more involved. This requires a little pencil and paper. You can figure it out. Okay. We'll do another policy now called shortest job first, and its variant called shortest remaining time first. Okay. So we've done the straightforward policies. Now we are going to look at some policies that do something that tries to optimize certain aspects of the system. Okay. Shortest job first, we'll start with SJF or shortest job first. Very straightforward policy. It takes a look at all the jobs in the ready queue. Okay. Picks the shortest job. The shortest job is a job that needs the least amount of CPU time before it finishes. Okay. And it runs that job. Once that job is done, it looks at the ready queue again. Okay. Picks the next shortest job, whatever is the current shortest job in the ready queue, and it executes that job, and so on and so forth. So at any point in time, when the CPU scheduler runs, you look at the ready queue, okay, and you look at what is the length of each job. Okay, pick the shortest one, execute. Shortest job first is a non-preemptive policy. What that says is, once you pick the job, okay, and you pick the shortest job, you let it run to completion, unless of course it does I/O and gives up the CPU. Yes, question.
So when there's A, B, C, D jobs, when the shortest job is A, when you run it, and then there's another job coming, and then the shortest one, then you run the next shortest one. But the last one is longest, we will never run again. Like when the shortest one keep coming.
Can you repeat the
Like,
question? I'm sorry.
there's
I thought you asked
There's
one
a
question.
small job that keep coming to the queue,
Okay.
and then the longest one will not run, right?
Okay. So you are asking a question that relates to a problem that I haven't even talked about, which is the last disadvantage there. So the question is, if there's a steady stream of short jobs arriving in the system, okay, what happens to longer jobs? Because there's always a shorter job to run. Let's say there's a job that needs 10 seconds, okay? And there is steady stream of short jobs that need 1 second that keep arriving. So you pick the 1 second job. As soon as it finishes, another 1 second job is running. It gets to run and so on and so forth. Okay? So as you will realize, what this leads to is a problem called starvation, where short jobs can cause long jobs to starve. Long jobs do not get a turn to run on the CPU because there is always a shorter job that gets favored over the long job. You are favoring short jobs. There are always a steady pool of short jobs. The long jobs don't get to run. But the policy says always pick the shortest job. Okay? That's a disadvantage of this policy. That long jobs are actually discriminated against, and they can in fact starve. Starve means they don't get to run on the CPU. They just sit there waiting for their turn and they never get a turn. So there's somebody always who seems to be favored over. Yes.
Also, there are processes that run infinite time, right? So first come, first serve.
Yes, of course. So if you have a non-preemptive policy and you write a process that's an infinite loop, you are in trouble. No other job gets to run. So this job is always going to keep running.
So there's just so nobody does that.
So if you have a non-preemptive policy, you better make sure that jobs will finish. If the job doesn't finish, then the rest of the system is nothing will run. Okay? So that's why preemptive policies actually are fair. They give each task a chance to run on the CPU. You don't just sit there waiting for a job to finish. It never finishes and then nothing else happens in the system.
How do you guess how long a job will take? Is it just depend on instructions?
Okay, that's a good question. The question is, how do you know the length of a job? Yeah, that's a good question. We'll come to that in just 1 second. Okay, so before we talk about the length of the job, let me talk a little bit about advantage. Okay, so shortest job first is a policy that has provably optimal waiting times. Okay, in terms of waiting times of the job, and we figured out how to compute wait times, completion time minus job length. Okay, this policy is the optimal policy. No other policy can do better. You can prove this. I'm not going to present the proof here, but you can prove that shortest job first is optimal in terms of minimizing wait time. Minimizing wait time was your goal. This is the policy to pick. No other policy can do better than shortest job first. Okay. And then before I come to that question that was raised, I'm going to talk about SRTF, which I did not mention. SRTF is a preemptive version of shortest job first, where you do have time slices. You pick the shortest job. If you give it one time slice, at the end of the time slice, you basically pick the next shortest job. If this job continues to be ready to run, you will pick the same job again until it finishes. Okay, so its shortest remaining time first is what is called SRTF. It is a preemptive version of shortest job first. And the way it works is, when you pick the shortest job, essentially the shortest job is the job that needs the least time to finish, the shortest remaining time to completion. You pick that job. You run it for one time slice. At the end of that time slice, you look at all the ready jobs. This job was the shortest job when you picked it. Now it is an even shorter job because it ran for one time slice. Okay? If no other jobs have arrived in the system, this job will continue to be the shortest job. Okay? So you'll continue to run this. But if some even shorter job comes, you will pick that job. So it is time slice. But in the scenario where no other jobs are arriving, it will do the same thing as shortest job. But if there are job arrivals, then you may actually pick a shorter job.
If we assume that there is no stream of incoming jobs, then shortest job first has no problem with starvation, does it? Like every process will.
If you have a static number of jobs, there are no issues with starvation because the last job, the longest job will get to run. That's the last job to run, and it will finish. Starvation problem comes up only if there are new arrivals in the system.
Cool.
Yes.
What if there are two jobs that have infinite loops?
Have what?
Just run forever.
Yes, if you have jobs that run forever, no policy can do anything. No preemptive non-preemptive policy can do it. It doesn't matter whether shortest job or FCFS. The job that gets to run is going to just take over the system and not actually let anything else happen. Yes, question.
If you're running a longer job, and a shorter job comes in the queue, we'll switch to that job.
Okay. Question is, if you're running a long job and a shorter job comes in, will you switch to that job or not? That depends on whether you're SJF or SRTF. Shortest job first is non-preemptive. You cannot interrupt a job, regardless of what else has happened. And shorter job could have come in, that's too bad. The short job that's running gets to run. Shortest remaining time first is preemptive. Okay? It runs for time slices. So at the end of the time slice, you get to make a new decision again. At that point, if an even shorter job has come in, it will get to run. Okay, so now we'll come to the question of how do you decide the job length. So now you have to make these decisions based on the length of a job. How is the OS to know what is the length of a job? Yes.
Based on the number of instructions.
Okay, based on the number of instructions. Is that a good metric to decide? Longer programs take longer to run. If you have a loop that doesn't tell you what instructions, don't tell you the length of a job. You could write a for loop, you use million times, it has one instruction in there. It's a very short program, but it's going to run for a long period of time. So looking at the length of your program is not a good indicator of the job length.
You can benchmark it, past experiences.
Yeah, so you could benchmark it, you could look at what has happened in the past and assume that the process is going to behave similarly in the future and make an educated guess. Last time this job ran, it took 35 milliseconds, 35 seconds. Maybe this time it runs, it will take approximately. So you could make a guess. Of course, you cannot make, you will never know for sure because what happened in the past may not happen now. You could have taken some input and executed based on that input. If the input changes, the execution times will change as well. Okay? So the length of a job is something that you can at best estimate. You will never know. When you start a mail client, You don't tell the OS, I'm going to run this client for the next 5 minutes and 30 seconds and then quit. Okay, the OS doesn't know this information, neither do you, the user. Okay, so the OS has no idea what the length of a job is going to be. Okay, it can make guesses, but guesses are only guesses. Okay, they are not accurate information. Okay, so one main disadvantage of shortest job first is you cannot actually implement it in practice in any reasonable way. Because it requires knowledge of the job length and you have no precise way to determine knowledge of job. That requires you to know what the future is going to be. So you can use past history and make educated guesses, but as I said, that's only estimates. You will never know. So shortest job first, the main limitation is probably optimal for wait times. The main disadvantage is you cannot actually implement this process or this scheduling algorithm in practice, because the OS doesn't know what the job length is going to be, and the process arrives in the system, it doesn't know. You can guess, but you don't know. That's a difference. Okay, so now we are going to add a column to our example and try to run through SJF shortest job first. Okay, same example as the previous one, 5 jobs, length 40, 50, 40, 30, 20, 10. Now we are going to use SJF. Okay, so you can figure out what happens, which job gets to run first. This is non-preemptive, so no time slices. Okay, here you are told the job length, okay, so it's not impossible to do this actually. Okay, so what's going to happen first? Which job gets to run? Okay, you are going to pick the shortest job. Okay, the job lengths are known to you, so you pick the shortest one. 10, job 5, which is length 10, is the shortest job. You'll run it to completion. Okay, so it's going to finish first. Then you'll take the next shortest job, which is job length 20. Run that to completion, and so on and so forth. Okay, so in this case, you'll actually execute them in the order 5, 4, 3, 2, 1. That's the order of the length of the jobs. So that's basically what's going to happen. So you will see that as a result of doing this, if you look at the wait times there, okay, so wait time is simply the difference of these two columns. Okay. So you see wait time for the 5th job is 0 because you picked it, they all arrived at time 0. Okay. This job ran for 10 seconds, so its wait time is 0. This job finished at time 30, it executed for 20, its wait time is 10. Okay, this job finished at 60, its length was 30, its wait time is 30, and so on. So you have wait times of 100, 60, 30, 10, and 0. If you take an average, you get a wait time, average waiting time is 40. And you will see that in this example, which is not approved, but in this example, the waiting time of shortest job first is half of that of round robin and FCFS. And as I said, you will basically optimize wait times, and this is just illustrating how it is done. You are favoring short jobs over long jobs, so you will spend less time waiting. Okay, so we will end it here for today. We'll continue with the next policy next week.